Hi guys, welcome to our newest video on Kinemarc. In this video, we are going to explore phasors and how the phases of currents and voltages behave when the current is passing through or the voltage exists across elements like inductors, pure capacitors, and pure resistors. And finally, we have a piece of magic that we are going to give you at the end of this video so you can quickly apply these principles in a jiffy when you're solving any circuits. So we are going to start our exploration with inductors. If you have an inductor, we know that the voltage across an inductor is given by V being equal to L di dt. And this current is, of course, the current passing through the inductor. By taking a reference current, by reference, I mean we are setting its phase to 0. We are going to have the maximum value of this current because these currents and voltages, they have frequencies. So its maximum and then its phase is 0 because we are taking that to be our reference. By substituting I into the V equation we have up there, we have our V to be equal to L multiplying the derivative of this I with respect to t. So if we differentiate this equation with respect to t, we are going to get omega cos omega t, and of course we still have our constant. And then cos of anything at all is the sine of that plus 90 degrees. So our cos of our omega t will simply be equal to the sine of omega t plus 90. And I'm going to show you this using a calculator. We see that cos of 2 gave us 0.99 and cos of 90 plus 2 also gives us 0.99. So indeed we have that to be true. Same thing, we'll try for a negative number. Cos of negative 5 gives us 0.996 and sine of negative 5 plus 90 also gives us the same thing, 0.996. So cos of omega t is going to be equal to sine of omega t plus 90. Based on that, we have our V to now be equal to. Now, take note, this small v we have here is our instantaneous voltage, the voltage across this inductor at any time t. So we also do represent this as V equal to our maximum voltage and then whatever its phase is going to be. But when you compare the small v we have here to this expression, this is going to be our maximum voltage because the instantaneous voltage is always the maximum voltage and then multiply the sine or cosine function here, which defines our phase. So we can see that our maximum voltage is going to be equal to L Im times omega. Let me rewrite that. So from here we can see that our voltage is equal to the product of omega L and our maximum current. So the voltage is going to lead the current by 90 degrees, or the current is going to lag our voltage by 90 degrees. Moving on to capacitors, the current in any capacitor is given by I equals C dV dt. Again, this voltage is the voltage across the same capacitor. And like we did in our earlier video, we are going to define our voltage, instantaneous voltage, as the maximum voltage having a phase of 0, so omega t plus 0. And then substituting this voltage into the instantaneous current equation above, we have our current to be equal to C times the derivative of this. So by differentiating this with respect to t, we're going to have, and again like we did, the cos of A is equal to the sine of A plus 90. So we will write this as sine of omega t plus 90 degrees. So by comparing this with our traditional instantaneous current being equal to maximum current times the phase expression, we can see that this expression right here is going to be our maximum current. So we rewrite this. Then from here, just like we had earlier, we can see that our maximum current is equal to the product of omega c and Vm. So we are going to have our current leading our voltage by 90 degrees, or our voltage lagging our current by 90 degrees. So moving on to a pure resistor, again we are going to define a reference voltage. Our instantaneous voltage is equal to the maximum voltage sine omega t, a phase of 0. And then from Ohm's law, so the substitution, so we have our maximum voltage with zero phase divided by the resistance. And again, we see our current being equal to this expression Vm over R sine omega t. Following our traditional notation of the instantaneous current being equal to the maximum sine the phase expression, we can see that this is going to be our maximum current. So our maximum current is equal to Vm over R. Unlike the earlier instances for inductors and capacitors where we had Vm or Im being multiplied by omega, here there is no multiplication by omega, so our current is in phase with our voltage for a pure resistor. There is no phase difference between them.
Right, so up next is the bonus we promised, but before that, this video has been sponsored by Sultan. Let's check this out.
Sultan, vitalizing drinks made from millennial old secret of black seed. Available in 4 flavors. Sultan drinks, you know what you drink.
So it can be quite tricky, memorizing whether the current leads the voltage or the voltage leads the current, and in the heat of exams this could be problematic. So you can easily remember these points by just having this magic word civil. C in civil stands for capacitors, and L, we usually represent inductances by L. Now you see that for C, immediately after the C we have I and V. So we read from left to right. So from here you can see that I leads V. So in capacitors, the current leads the voltage, and it's always by 90 degrees in a pure capacitor and inductor. The same thing for your L. You can see from here that attached to the L is V and I, but the V reading from left to right leads the I. So you can say that in inductors, the voltage leads the current by 90 degrees. So all you need to do is to remember that for resistors, and for resistors they are in phase, so that's pretty much made easier by civil. Thank you very much for watching our video. We hope it was helpful. Do also check our other playlist on applied electricity. There are other helpful videos there too. See you next time. Bye.